Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And hi everybody. Guys, how are you today? Today topic is about air standard cycle. Okay, and we are in the chapter number 5. So first of all, I would like to make an acknowledgement to my friends in UITM Shahlam for their efforts of prepared this slide. Thank you very much to Dr. Idris Saad, Dr. Al Hassan Salami, and also Dr. Noor Afifah Yahaya. Today's topic will be divided into several parts. Okay, so this is part one for chapter number 5. So in this chapter, the objective that or you should be able to know, evaluate the performance of power cycle for which the working fluid remain a gas throughout the entire cycle. And the objective of number 2, what you should know is you should able to develop simplify assumptions applicable to the gas power cycles. Okay, so for this part one, there are only two objectives that you have to take notes. Part 1, chapter 5, air standard cycle. Okay, in this chapter, part 1, I will give a lecture based on the introductions to power cycle. Number 2, basic considerations in the analysis of power cycles. Number 3, the Carnot cycles and its value in engineering. And number 4, air standard assumptions. That is for part number 1. Okay, students, may I proceed for the lecturing? Okay, let's look on the introductions of power cycles. So in the thermodynamics, for the applications, there are two important areas that we will be covered. The areas are power generations and also the refrigerations. So as you know, or as you have learned previously in chapter number 1 to chapter number 4, the device or the system used to produce a net power output are often called engines. And in thermodynamic cycles, they operate on are called power cycles. So the thermodynamic cycles can be divided into three categories. Number 1, gas or vapor cycles. That means you will learn about the gas cycles. That gas cycle, what it means? It means a working fluid remains in the gases phase throughout the entire cycle. For the vapor cycles, it means the working fluid exit in the vapor phase during one part of the cycles and in the liquid phase during another part. Category number 2, closed or open cycles. Closed cycles actually is for the working fluids is returned to the initial states at the end of the cycles and it's recirculated. Okay, that is a closed cycles. And for the open cycles, you must know that the working fluids is renewed at the end of each cycle instead of being recycled. Okay, that is the difference between closed and open cycles. And category number 3, internal and external combustion engines. For external combustion engines, what you have to know is uh, heat is supplied to the working fluid from an external source. Okay, and in if we call internal combustion engine, it means that heat is supplied by burning the fuel within the system boundaries. Okay, there is difference between external and internal combustion engines. Okay, so as I mentioned here, in generally, these thermodynamic cycles are complex. So therefore, various gas power cycles are analyzed using some simplifications. So this is a flow of the heat engine. Okay, remember in chapter number 4, that's mean in the second law of thermodynamics, you have learned about heat engine. Okay, heat engines can be divided into external combustions and also internal combustion. So for the external combustions, example from steam engines, and for internal combustions, the engines reciprocating vehicle and also rotary gas turbine. So for reciprocating, we have two type of engines. That's mean CI engines. Yeah, that's mean compression ignition engines. SI engines. That means spark ignition engines. And these two engines, the process of this engine can be divided into two-stroke or four-stroke. Okay, for this thermodynamics one, we will focus more on the four-stroke engines. Okay, as I mentioned, uh, the device of the system applications of thermodynamics based on the heat engine is quite complexity. So basic considerations in the analysis of power system cycles must be done. Okay, so as you see in the graph of pressure versus specific volume, there are two cycles. Okay, the red one, the straight line of the red one, and another one is the green one, the dot line of the green one. Okay, the red one is the ideal cycles, and the dot line is the actual cycle. Okay, as you see at these two cycles, you can notice that for the actual cycles, it have a curved line. Okay, compared to the ideal cycle. Okay, so when you want to do the analysis based on the calculations, actually we have to consider the ideal cycles. Okay, not on the actual cycles, because the actual cycle is quite complex to do the analysis. So we assume, or we make the considerations or assumptions based on to the ideal cycles. So what it means, okay, the cycle encountered in the actual devices are difficult to analyze. So what as I said just now, because of the presence of the complicating effects such as frictions, okay, and the absence of sufficient time establishment of the equilibrium condition during the cycle. So to make this analysis study more feasible, we have to keep the complexities of the manageable levels and utilize some idealizations. Okay, so this called the modeling the cycle. So if the cycle resemble of the actual cycle closely, but it made up totally of internally reversible processes, and this called as the ideal cycle. So ideal cycle actually the internal reversible, but unlike Carnot cycles that you have seen in the chapter 4, they are not necessarily externally reversible. Okay, therefore the thermal efficiency of the ideal cycles in general is less than the of the total reversible cycle operation between the same temperature limits. Okay, please keep in mind that's sentences. However, okay, it is still considerable higher than the thermal efficiency of the actual cycle because of the idealizations utilized. Okay, so the cycle discussed in this chapter are somewhat idealized, but they still retain the general characteristic of the actual cycles they present. Okay, so the thermal efficiency of heat engines, the formula, if we want to find, is based on the new thermals is equals to work net over heat in, okay, or work net, specific work net over specific heat in. Okay, this is a thermal efficiency for heat engine. Okay, if you want to, if you have to find the thermal efficiency. This the simplifications of the power analysis, power cycles analysis can be summarized, okay, as follow. Okay, three factor that can be introduced or can be considered in the analysis of power cycles. Number one, the cycle does not involve any frictions. Okay, that is you have to remember. The cycle does not involve any frictions. Therefore, the working fluid does not experience any pressure drop as it flow in the pipes or device such as heat exchanger. Okay, we don't consider any frictions. Number two, all expansions and compressions processes take place in a quasi-equilibrium manner. Okay, and number three, the pipes connecting the various components of the system are well isolated. Okay, that is assumptions that we will must make, and the heat transfer through them are negligible. Okay, so we also neglecting the changes in kinetic and potential energies of the working fluids commonly used due to the devices that involve shaft work such as a turbine, compressor, and pump. The kinetic and potential energy term are usually very small, okay, because it's very small relative to the another term of energy equations. That's why we neglect kinetic and potential energy. The only devices where the change in kinetic energy are significant are in the nozzle and diffusal. Okay, please remember, if you calculate the nozzle and diffusal, or you make the analysis of these two devices, you must consider kinetic energy. Okay, so the properties diagram such as PVTS diagram as shown, okay, at the right side, have served a valuable aid in the analysis. So as you see here, PV diagrams, okay, state number 1 to state number 4, what happened in under the graph is the work net for that cycles. If we plot TS diagram, it will show like that, number 1 to number 3. Okay, number 1 to number 3. I will highlight. Okay, number 1 to number 3 and number 4. Okay, all the under the graph. Okay, under the graph lines is work net for TS diagram. Okay, now we look on the Carnot cycle and its value in engineering. Okay, Carnot cycle also you have learned in chapter number 4. I have introduced it to you in chapter number 4. If you don't remember or you not remember, please find it in my YouTube channels, and also you can review again. Okay, about that chapter number 4. Okay, actually the Carnot cycle is composed of 4 totally reversible processes. Okay, remember I said just last time in chapter number 4, we have 4 processes in Carnot cycles: isothermal heat additions, isentropic expansion, isothermal heat rejection, and also isentropic compression. Okay, as you see here in the graph, the S diagram. So this is the rough picture of the Carnot cycles. Okay, I have 2 isentropic processes and 2 isothermal processes. Okay, have you and for both ideal and actual cycles, thermal efficiency increases. Okay, with an increase in the average temperature at which heat is supplied to the system, or with a decrease in the average temperature at which heat is rejected from the system. So the pictures, the schematic diagrams of the Carnot engines can be drawn such like this. Okay, so there are 2 compressor, because this is a air standard cycle, so 2 compressor and also 2 turbines. Okay, one is isothermal compressor and the one is isentropic compressor, and another one is isothermal turbine and isentropic turbine. Okay, this is for air standard cycles, because the working fluid is a gas, that means air. Okay, air standard cycle. So to calculate the efficiency of the Carnot cycles, also the formula you can use is 1 minus TL T low over T H. So because these operations of Carnot's engines in between maximum and minimum temperature. So the high temperatures is a maximum, the low temperature is minimum. Okay, the operation is between these two levels. So upon the revisions of the performance of real cycles, often mentioned in terms of thermal efficiency. So when we derive it based on the thermal efficiency of the engines, or the heat engines, we know that the general equations is W net over Q in. So W net is Q out minus Q in minus Q out. So we simplify these equations. Then we also know that Q out is equals to TL S3. Okay, Q out, this process Q out is TL times by S3 minus S4, and it's also equals to TL S2 minus S1, because S2 is equal to S3, S4 is equal to S1. Okay, so put in the rearrange this all the formulas in thermal efficiencies formula, and lastly you will get 1 minus TL over TH. Okay, this equation is also same as what have you know and learn and see or what has been I introduced in chapter number 4 for thermal efficiency for Carnots. Okay, this is an important thing in chapter number 5. Okay, the assumption that you have to know when you want to do the analysis based on the device or devices that use air as a working fluid. Okay, or instead of air, it will use a gas. Okay, that's mean the gas phase. Okay, in power engines, energy is provided by burning fuel within the system boundaries. So, example as internal combustion engines. And for this reason, okay, the assumptions known as the air standard assumptions must be applied. Okay, there are four uh, assumptions that you have to apply for this case. Number one, the working fluid is air, so continuously circulated in the closed loop and also behave as an ideal gas. So remember, behave as the ideal gas. So when it behave as the ideal gas, so the equations, the formulas that can you use to analyze, to make the analysis or calculate in the device that use air, you can use ideal gas approach. Okay, or the formula that's mentioned in the ideal gas. Number two, all the processes that make up the cycles are internally reversible. Okay, please remember. Number three, the combustion process is replaced by heat addition process from an external source. And number four, the exhaust process. The exhaust process is replaced by heat rejection process that restore in working fluid to its initial state. Okay, for the combustion process, it replaced by heat addition process. For exhaust, it replaced by heat rejection process. That is an assumption that we do when you want to analyze the gas power cycle. Cool air standard assumptions. When the working fluid is considered to be air, so the constant specific heat at room temperature we can apply. Okay, so at room temperature we consider 27 Celsius, approximately 300 Kelvin. So if you don't remember this, or so you can find in the steam table properties. Okay, in the table, in the first table, that's meaning it have Cp, Cv, and K. And another one is air standard cycle. What it's mean? It's mean the cycle for which the air standard assumptions are applicable. Okay, that is air standard cycle. That's all for this part one, chapter 5. So there are only two objectives you have to know, and we will see in next video about air standard cycle. Okay, in part 2. Okay, thank you very much for listening. Hopefully you understand the considerations and also the assumption that you have to do when you make the analysis of power gas power cycles using air standard cycle or using air. Okay, thank you very much. See you in next lecture.